Welcome to the Data Science Institute's virtual seminar series. My name is Dr. Sarah Mackey from Lawrence Livermore National Laboratory. Here at Lawrence Livermore, data science has become an essential discipline in many of our key program areas. LLNL is home to many challenging datasets, as well as home to some of the world's most advanced supercomputers. Our data science staff work in a variety of areas, including machine learning, artificial intelligence, big data analytics, statistical inference, predictive modeling, and uncertainty quantification. The Data Science Institute acts as a central hub for our lab's data science activities. We host events like this seminar series in order to introduce new ideas and potential collaborations to our laboratory staff. We invite speakers from outside the laboratory, from the Bay Area and beyond, to share their innovative approaches with our data science community. We're pleased now to include a wider audience in our seminar series through these recordings. You can read about past speakers at our website at data-science.llnl.gov, or you can email us at datascience@llnl.gov. Thank you and enjoy the seminar series. So today we'll hear from one of our own. We have Ming Jiyong. Ming's a computer scientist in the Center for Applied Scientific Computing at LLNL. His research focuses on applying machine learning to automate simulation workflows and exploiting big data analytics for HPC simulation data. Ming first joined LLNL in 2005 as a postdoc researcher in CASC, and that was after he received his PhD in computer science and engineering from The Ohio State University. He's been a principal investigator and project task lead on several large-scale collaborative research projects, including machine learning for ALE simulations, data-centric architectures, and real-time space situational awareness. His research interests include scientific machine learning, data-intensive computing, multi-resolution analysis, and flow resolution. So Ming, thank you for joining us today. And when you're ready, go ahead and take it away.
Thank you, Sarah, for the wonderful introduction. So folks, as I get into my talk, I'm gonna turn off my webcam. I was telling folks earlier, I've been having some trouble with my webcam. I'm just gonna unplug it. Okay, so right about now. Okay. All right, so hi everyone. Glad you can make it to my talk. Today, I'll be sharing with you some of our experiences from using Apache Spark, which is this big data framework for doing machine learning on large scale or massive HPC simulation data. Folks have been trying to use Spark on HPC systems for a while now. We're certainly not the first, but the data scale at which we're trying to do this is unprecedented. When we try to use Spark at this scale, we uncover some really interesting aspects of Spark that folks haven't noticed before. In fact, what we uncovered kind of goes against the grain of the state of the practice of using Spark on HPC. So in this talk, I'm going to share with you some of those best practices we distilled from our research experience in doing this work. This is done in collaboration with Brian Gallagher, Galeb Abdullah, Al Chu, as well as Timothy Bender. Okay, now this talk may be a little bit different from your usual DSI seminar talks. I'm not introducing a new deep learning framework, a new machine learning algorithm, or even a new application. In fact, the application I'm going to be talking about has been well known around the lab for a while now. Instead, it's going to be more focused on how to use this existing well-known tool on our HPC systems and basically some simple tricks. Okay, I'm going to frame this that way. But the important thing here is I'm going to show you why these simple tricks work and why they're important. Okay. As Sarah said, feel free to interrupt me. By all means, you can just unmute. If you want to type in questions in chat, please do so. Sarah will interrupt me. I prefer a much more interactive talk than these WebEx ones, but it is what it is. Okay. So, as you all probably know by now, machine learning is being used everywhere. Not surprisingly, there's been a growing interest in using it for HPC simulations. The problem is HPC simulation data can be massive, and deploying machine learning algorithms at that scale is hard. Big data frameworks like Apache Spark offers an attractive solution to this problem. It's heavily used in the industry for a wide variety of applications, and it can scale, especially on dedicated big data clusters. Of course, there are still some major challenges in using big data on HPC. For instance, big data clusters tend to have large amounts of no local storage, whereas that's not the case for commodity HPC systems. Those systems tend to rely on network storage, which can really slow down the performance of traditional big data workflows. So the question becomes, how practical is it for everyday HPC users to use big data frameworks? In this talk, I'm going to try to answer this question with the focus on massive HPC simulation data. Okay, so first, let me motivate this work by using a real-world HPC application that we care about. Arbitrary Lagrangian Eulerian, or ALE, simulations are used in many scientific engineering applications. ALE simulation codes are vital to the DOE stockpile stewardship science. Now, the problem with ALE codes is that they can suffer from failures that require users to tune a lot of knobs and parameters to complete a simulation. Developing strategies for how to tune these parameters is often a trial and error process. Once a user sets up a simulation, they run it, and at some point it unexpectedly crashes. The user must then determine what and where the failure occurred and adjust these knobs and parameters accordingly to avoid it in the next run. Obviously, this can be very disruptive and time-consuming. A few hours of simulation can require many days to tune. A good example of these failures are mesh tangling, which is shown here on the right. You can see that this is where a mesh element can be driven by the underlying physics until it gets all twisted and bent out of shape, literally. At that point, it's geometrically bad, which means it's numerically bad, and that's when the simulation crashes. Now, our objective is to use machine learning to avoid these failures and automate the ALE codes as much as possible, for this part at least, so that we can reduce the time and effort it takes users to produce solutions. Okay. So we've been working on this, working on developing machine learning framework to, semi-automate these ALE simulations for a while now. In one of our approaches, we train a random forest regression model to predict the conditions leading to these mesh tangling failures. Now, to do this, we had to generate a lot of training and testing data. Okay. So we developed a procedure that can trigger these mesh tanglings by running the simulation in basically the pure Lagrangian mode. You don't have to worry about the details here. We apply this procedure to an ensemble of simulations by varying the initial conditions of it. So basically, for the well-known bubble shock simulation, which you see here on the bottom, we varied both the piston speed that drives the simulation, that pushes the bubble, as well as the bubble density. Okay. Now, since the procedure is dependent on the simulation, to our surprise, we ended up generating over 76 terabytes of single precision simulation data. When we calculated the number of learning examples in that data set, it turned out to be over 1 trillion with a T. At that time, this was back in the 2016 timeframe, we had no way to train on all 76 terabytes of data. We were using scikit-learn, which you guys probably know. It's a very popular machine learning library in Python, but it doesn't really do parallel distributed. So we were only able to train on small portions of our data set back then. But in the back of our mind, we kept on wondering, how are we ever going to train on all 76 terabytes of data? Okay, do this. Well, as you probably guessed, training machine learning on that much data on an HPC system is not easy. You essentially have two choices. One, you can write your own custom solution, which means you have to have a distributed machine learning algorithm that's implemented in a parallel application. With these one-off solutions, you can easily tune the code to perform well on your system, but it's going to take some R&D investment to get it going. The other choice is to use some kind of off-the-shelf solution, such as a big data framework like Apache Spark. Spark offers data analytics at scale. It allows you to perform things like SQL queries, data streaming, graph analytics, and the one we really care about, machine learning. More importantly, it's open source and community supported, so we don't have to pay for anything essentially. Okay, here I'm going to rattle off a few more attributes about Spark. In terms of speed, it can persist to memory and/or disk for fast computation. In fact, this is the crux of the issue that I'll be addressing for the rest of my talk, okay, speed. So please keep this in mind. Now, in terms of simplicity, it offers a rich set of APIs using Spark's implicit data parallelism. What this means is that as a user, I don't have to worry about which procedure I need to run on which piece of data. That's all handled for me underneath the hood. And finally, for support, Spark has APIs in multiple programming languages like Java, Python, Scala, as well as a variety of database systems. Okay, so all these makes Spark a very attractive choice. So why is using big data frameworks on HPC systems a major challenge? Okay, here I'm going to dig into this just slightly. The big data ecosystem is very different from the HPC ecosystem. Now, for this sort of rough high-level comparison, I'm going to go through, keep in mind that this is done with broad strokes, so there are obviously exceptions to everything I list here. In terms of storage, big data clusters have abundant node local storage, whereas commodity HPC clusters rely mostly on network storage. As for hardware, big data hardware are usually optimized for I/O, whereas HPC hardware tend to be optimized for MPI plus X. Spark uses a yarn scheduler, whereas Slurm tend to be the de facto for HPC. And finally, with networking, it's Ethernet for Spark and InfiniBand for HPC. Now, there's been quite a bit of research on resolving these differences one way or the other to enable HPC plus Spark. These work include integrating Spark into HPC applications like high energy physics, performance tuning, and porting onto specific HPC systems like the Cray XC system. You also have developing novel I/O frameworks around Spark, like Glean or H5 Spark, and of course the usual scaling Spark with more and more cores. The strong scaling story, if you will. In contrast, our work is focused on providing a set of simple best practices for everyday HPC users so that they can run these big problems too. Okay, one of the key findings from our work is that data scale matters. And it matters because it forces you to use Spark in a way that kind of goes against the grain of what the state of the practice recommends. Okay. Alrighty. Now for our Spark application, our data size is 2 to 3 orders of magnitude larger than what's been published in the literature, which means we need a distributed machine learning algorithm that can work at our scale. Now, to demonstrate Spark capabilities, we have 2 real-world use cases from our application. One, the random forest, which is for supervised learning for failure prediction. This is a direct extension of our previous work using scikit-learn, but at a much larger scale using Spark. This use case involves calling a single complex function whose implementation we cannot easily modify. Now, it simply consists of reading in the data and then calling the random forest function. That's it. Okay. For the second use case, we call it failure mode analysis. This is for unsupervised learning using k-means clustering. Okay, we developed this analysis pipeline in order to have a better understanding of the failures, and in particular, whether or not there are distinct classes or modes of failures. So this use case involves setting up a pipeline of these lightweight functions to analyze failures. It consists of reading the data, then applying data standardization before calling k-means clustering, and finally computing the silhouette scores. Okay. Any questions so far? I hope I haven't bored too many people. Any questions on our setup while we were doing it?
So, Ming, on the previous slide, you have both supervised learning and unsupervised on the same trillion data set sample, or these are
Yes.
different data sets?
On the same data set.
So your trillion sample data sets are labeled.
Our previous data set are what? One more time.
They are labeled. They are supervised. You're doing supervised learning on that.
Yes. Yep. On.
Okay.
Yep. On. I mean, I'll show you experiments. We ran it from 10 terabyte, 20 terabyte, 40 terabyte.
So did you ever figure out how many data samples you actually need for the training to converge, or you have to?
Yes,
you need
we
that
do.
many samples?
Yes, that's one of the questions we were trying to answer is how do we, obviously, we probably don't need the full data set. What is a good, effective sampling strategy for our application was one thing we wanted to answer. Of course, one way to answer that would be to get the actual answer from the full data set and then try different sampling strategies to see which one works better.
Okay.
Yep, which means we need an answer for the full data set first.
Hi. I just want to make sure I'm on the same page before we move forward. So
Yes.
I'm understanding this right. You're using the random forest to determine, which ones are failures or not, failure detection, prediction. And
Yes.
then you're feeding that into your k-means clustering to cluster it into various types of failure after you've determined which ones are failures.
No, they're two different things.
Okay.
They're two different things.
Okay.
They don't feed into each other. They
Okay.
both operate on the raw data.
Gotcha.
They both
so
operate on the raw data.
So then what was, I guess I'm a little confused what the purpose of the second one, the k-means clustering, was. What were you trying to accomplish with that?
We wanted to know how many failure examples do we really need. Maybe just one. Maybe if we have one failure example, we can use that to run any problem. Is that true? Maybe they all look alike, quote unquote. Is that true? That's what we want to find out. We want to find out, and of course, there are other issues as far as a noisy label situation. There are other almost failed mesh elements that did not exactly fail, but geometrically speaking, they were really bad. Finding them was equally as important as the ones that we were told failed. So you can imagine this is sort of a very coherent process where these elements are getting driven and compressed and twisted. Some of them twisted and became bad, and the simulation code recognizes, oh, negative area, negative volume, you are failed, stop, everything stops. But there are other mesh elements, its neighbors. You can imagine some of the elements right next to it. They were pretty bad too. It's just they weren't exactly on the negative volume area side to be labeled as bad. So we want some way to be able to identify those elements as well, because right now, without knowing who they are, they're being incorrectly labeled. And so
Gotcha.
it was to address the labeling problem, we want to understand or have some other way to tell us, for example, here are the bad ones, here are the 90% bad ones, here are the 80% bad ones, here are just 50% bad. I mean, if you look at it, it wasn't exactly bad, but we knew it was going to be bad for 100 cycles from now, let's say. So we were
gotcha. So you're preempting the optimization for the AIL code before it becomes a problem by labeling less bad things.
In fact, we had to.
Gotcha.
The way to avoid some of this is to apply mesh relaxation, this procedure they called, to adjust to fix it essentially. But you can't do it when it's bad. It's because all the physics have been polluted already. You got to start applying this well before it goes where it looks bad. Let's say. How soon ahead to do it is sort of the crux of the issue.
That makes a lot more sense now. Thank you.
Okay. Sorry, these things I explained it so many times now. It's clear in my head, but when I present it anew to folks, I don't always do a good job. Great questions. Any other questions? Okay. In the next few slides, I'm going to tell you a story about our initial attempt at using Spark on our application. I'm going to describe a very simple experiment we thought should have easily worked, but didn't. And then I'm going to tell you what we learned from that experience to formulate this set of best practices. Okay. All right. So first thing first, we use Magpie to set up the environment to enable Spark on our HPC system. MapReduce is developed here at Livermore by Al Chu and supports many big data frameworks and schedulers and HPC resource managers. It's robust, open source, and actively supported. If you were interested, please check out this link. Okay, so we try to train a random forest model using 32 compute nodes for up to 2 terabytes of data. Okay, and this was done on the Livermore Catalyst system. This is a very old system, but it has node local SSDs. Okay. So the original data resides on network storage, or Lustre in this case. This is very typical for post-processing simulation data. Okay. And of course, following the state of the practice recommendations, we did not use compression and we persisted to these SSDs. Okay, so that's our initial experiment setup. Now, the graph here shows you the average disk utilization on those 32 SSD nodes. Okay, so that line's the average, and the air bars are the min and max. It depends on which node. So for the half terabyte, it finished within half an hour. Great. For the 2 terabytes, no, it finished within an hour. Sorry. For the 1 terabyte, it took 2 hours. Great. And then when we ran the 2 terabyte data, we got a rather shocking fatal out of disk error. Now, keep in mind, this was done on 32 Catalyst nodes. So to do the math, we have more than 27 terabytes of collective node local storage. So we're trying to do random forest on 2 terabytes of data using 27 terabytes of space, and we couldn't do it. So what the heck happened? Were we just stupid? Did we use it wrong? Did we set the wrong thing? Why can't we train a random forest on just 2 terabytes of data using collectively 27 terabytes of node local storage? To answer this, we analyzed the files on those SSDs while the job was running. And here's what we noticed, okay? During the Spark job, there are 2 types of files, RDDs and shuffle files. In terms of number of files, these are the blue lines plotted here. They're within ballpark of each other. You can see that the shuffle files varied more. But in terms of the total file size, that's the orange line shown here, there was a huge difference. For 1 terabyte of training data, the RDD files took up 12.6 terabyte of space. Okay, I want you to think about that. For 1 terabyte of data, we got 12.6 terabyte of intermediate files. The main issue here is with Rdd persistence. Okay, RDD is a fundamental data structure in Spark. Their usage is motivated by iterative or multipass algorithms. Okay, now one of the main advantages of RDD is that they can be persisted or cached to memory and or disk. So this allows you to save all your intermediate data, your intermediate computations for reuse, so that you don't have to recompute them each and every time. So obviously this provides a speed up over like Hadoop from 10x to 100x, which is great. Okay, this is all good. But Rdd persistence also has a downside. It can lead to this ephemeral data explosion of Spark intermediate files. 12.6 terabytes. Not surprisingly, there's a fundamental trade-off here between space and time. It takes time to read our original data from storage, and it takes space to cache the data locally, which is limited in space. Okay, so that's a trade-off we're playing around here. So what is causing this 12.6x data explosion? In order to quantify this, we introduced a new measure, which we call the X factor. Now, unlike that British TV show, this is simply defined as the ratio between Spark disk utilization and the original data size. I know it's kind of boring. It's not as fun as a TV show. So for the previous example, the X factor is 12.6x. Now we can observe the X factor in our scaling studies the same way we can observe runtime. Okay, this will become important for why we should do this. So where exactly does this data explosion come from in Spark? In other words, how do we end up with 12.6? We did some digging, and here's what we found. 2x is due to what we call data type inflexibility. Okay, this is all the data structures in Spark use double precision floats. Our data is stored as single precision simulation data. So we get 2x bump up right off the bat. Around 2x is due to the random forest implementation. So it has two persist calls. Remember, this is to cache data. One to cache original data on the SSDs, and the other to cache intermediate data. Okay. And then lastly, this leaves us with around 3x. This is due to Java object serialization overhead. Data is serialized when RDD files are written to disk. Okay. Now, one thing to note here is that this X factor is both data and algorithm dependent, obviously. So what can everyday HPC users do about these Spark data explosions? Well, adding new hardware to a system is not practical. You guys may know this. The procurement process is long and tedious. Customizing Spark software, like using single precision inside instead of double, it's also not practical. We tried doing this. We tried changing it with through one of our IBM collaborations, and after 3 months of trying, it did not go well. It's it's a rat's nest down there, basically. So what options are available? Well, if too much data is a problem, you can always reduce the data by compressing the RDDs. And if you want to avoid the out-of-disk errors on the no local SSDs, then you can use network storage instead. Okay. Unfortunately, both of these options are not recommended in the state of the practice. Here we're referring to both the Spark documentation and current literature in Spark in HPC plus Spark. So we simply ignored those recommendations. Here's what we noticed. Okay. On the top graph here, it shows you the runtime. We tried three things: the default uncompressed. We tried compression on SSD, and then we also tried Lustre network storage. Okay, and then the bottom graph is correspondingly shows the X factors as I introduced that notion. Okay, so in terms of runtime, the compressed and uncompressed, the blue and orange, they're very much alike. Notice at the 2 terabytes, it died. Okay, so you remember that was a fatal out-of-disk error. But before that, the blue and orange were very much alike in runtime. So there was no difference, which is what other folks noticed. But if you take a look at it from the X factor perspective, there's a huge difference between blue and orange. Okay, there's a huge difference. And this is one of the reasons why the X factor becomes important, because if you simply look at the timing alone, you would say, blue and orange, it's no reason to use compression. And we couldn't fault you for that if your setup is big enough. But from the X factor perspective, the difference is huge. So this suggests we need to update the state of the practice. And that's what we did. The main contribution of our work is an updated set of best practice for using Spark on massive HPC simulation data. What makes this work novel is that these best practices are in direct contrast to the state of the practice recommendations. Now, here's the key. Those prevailing state of the practice recommendations are ideal only for data that's small enough to fit in either memory or no local storage. Okay, clearly the 2 terabyte fit within the 27 terabyte, but we did not understand the X factor back then. Okay, so you have to do trial and error to make sure it runs or it fits and doesn't have these fatal out-of-disk errors. Okay, so as I mentioned already, our data size is 2 to 3 orders of magnitude larger than what's been published. And this is probably, we think, one of the reasons why folks didn't really notice this issue before. So for our best practices, we chose to focus on user configurable options in Spark. Okay, rather than telling people buy more hardware or modify Spark, we chose the user configurable options so that everyday HPC users can set them at the start of their job. Makes it very simple. Set this option, you're ready to go. Okay, so the advantage is that they're general, applicable to different Spark versions and configure yada yada. It's very simple to use. At a high level, our best practice can be summarized as 1, turn on compression, 2, use hybrid strategy, and 3, increase block size. Any questions on this so far?
Hey Ming, there's a question from Jeff in the chat. Question about the type of compression being used. Is it lossy or lossless compression?
It's lossless. In fact, I'll show you a couple experiments on what we tried. It's the standard LZ4 and then ZSCD level 1. I'll show you the experiments of what we tried. The take home is, if Jeff has to log off early, the take home is use ZSCD level 1. Both of these are offered inside Spark. Any other questions?
Is this compression applied before or after the serialization? And also, does it rely on like the 4-byte float format?
No, it doesn't change any of that. You have your double precision serialized. Instead of writing the serialized data out, you compress it.
Okay.
So yes, you're squeezing. So which is what you're saying. It's able to squeeze a lot out of that serialization, expensive serialization process.
Okay.
Again, this is how Spark gets implemented. Some of these are harder to change on our side. Any other questions? Great questions. Okay, in the following slides, I'm going to go through some experimental results to justify these rather contrarian best practices. First, I'll show the results for each of the recommendations themselves, and then I'll present some actual machine learning results, okay, that we were able to do with these best practices on Catalyst, which is a very old system. In fact, that's our bragging right. We can do this on Catalyst. Imagine what you can do on Sierra El Capitan. Okay, for the first user configurable option, we recommend enabling Rdd compression, which can be done using this Spark option. That's it. It's very simple. So Rdd compression is disabled by default. Now, the prevailing view is that compression can have a noticeable runtime cost with little to no benefit. This is only true if your Spark intermediate data can fit in no local storage. Okay. So we ran experiments comparing with and without compression, as well as with different codecs, LZ4 and ZSTD, which can be set using this Spark option here. Okay, that's it. So in the table below, you can see that for 1 terabyte of data, on the default, it took on 32 nodes, 1 terabyte, 32 nodes. The default uncompressed took 1.5 hours and 12.6x X factor. If you turn on compression but use a default codec, it just took 1.6 hours, but now the X factors went down to 4.1x. Both of these are lossless compression. And with ZSTD as the codec at level 1, it took, yes, 1.8 hours. There's a notable difference. That's true. But now the X factor went all the way down to 1.7x. Okay, so that's about 20% increase in runtime. So that is noticeable. And if you never had a notion of what X factor is, you would say, ugh, why would I want to pay 20% increase in overhead? But now with X factor, you will notice that that decreased by 87%. 20% runtime for 87% space, if you will. So the graph on the right shows you more comparisons between, this goes back to the question, LZ4 and ZSTD, blue, orange. The takeaway here is that they're very similar in terms of the runtime. And if you took your hand, cover up the bottom graph, for those of you, well, everyone's virtual, so cover up the bottom graph. If you only looked at the runtime, you would have concluded, it's not much difference, right? Default codec LZ4, ZSTD, I don't see the difference. But if you took your hand away from the bottom graph and took a look at the X factor, yeah, there's a huge difference. Which is another way to say, for very, very little cost, you get much more savings in your X factor. Which means this allows you to fit a bigger job onto your limited node local storage. That's a key takeaway here. Okay. It allows you to run a bigger job with the limited allocation you have for very little cost. Second option, okay, we recommend using a hybrid strategy for Spark scratch space. Now, what am I talking about here? First of all, Spark scratch space is for storing intermediate files. That's the thing that blows up. You can easily set this using the Spark option here. Okay, so you could point it at the SSD directory, the no local storage, or even Lustre, which is the network storage. Very simple to do. Okay. Now the table here compares the performance between SSD as well as Lustre, with and without Rdd compression. Okay. First, you notice that Lustre does take a longer time. This is clearly shown here. Okay. And which is well known. I mean, Lustre, SSD is local and fast, but limited in space, and Lustre is shared network storage and slow, but it has quote unquote unlimited space. Okay. So you get that savings, and of course, the corresponding X factors you clearly see. One interesting to note here is that for the same compression, the Lustre actually is even smaller. And of course, when we dig a little deeper, we learned, as folks from LC may know this already, our Lustre uses ZFS underneath the hood, which has transparent compression. So you get that extra compression from that. Okay, so it'd be great if we could try to use both. Use SSD as much as possible, and then if we have to, go to Lustre. Question is, how do we do this? How can we use SSD as much as possible and only flow out to this expensive and slow network storage if we don't have a choice? So here we introduce a hybrid strategy. This uses this lesser known feature where Spark accepts comma separated lists for scratch directories. That's it. Very simple. So what can we do? Sorry, I got to toggle this. If you provide 2 of these directories, Spark will treat them as round robin fashion. Okay. You use this option, it'll allow you to control how to combine SSD usage as well as Lustre usage. The graph here shows a weak scaling of results comparing SSD, hybrid, 50/50 hybrid, and Lustre. So here the hybrid is just 50 on SSD, 50 on Lustre. Okay. The takeaway here is that in terms of the runtime, because the hybrid strategy is exactly what we expect it to be, which is half the runtime. But now you get to utilize network storage only for half the stuff. So if you have a fixed number of nodes allocated to your job and you're not exactly sure if it'll fit, or it probably won't fit, but you can't wait anymore, then this is a simple strategy you can utilize to help offload some of the computation onto network storage and still utilize as much as your SSD as you can. You could probably come up with clever strategies to how to use this comma separated list. This is 1-to-1, so it gives you half each. Okay. Option number 3, we recommend increasing the block size for network storage persist. If you have to use network storage for persistence, what can you do to improve performance? Let's say you're not on Catalyst. Catalyst has SSDs. Let's say you're on Quartz. You don't have SSD. What can you do? In order to answer this question, we need to understand how Spark data partitioning works. So this affects parallelism. Okay. In Spark, partitioning data into blocks affects the number and size of intermediate files, as well as the number of tasks. So we know that for network storage, file count and size dominates performance. Okay, so Lustre I/O is a known bottleneck. We know that it performs better with fewer and larger files. Hence, it stands to reason that using larger block sizes in Spark should improve performance on network storage. Now, the challenge here was finding out how to change the block size so that the Spark intermediate jobs are affected. And this turns out was not easy. In fact, there were other previous publications that tried to do this, and they reported back that they did not see a difference. We suspect what they tried was not correct. Took us a while, but eventually we figured this out. Spark controls Lustre block size through this option here, fs.local.block.size. Okay. The graph here compares the runtime performance between SSD and Lustre on these 32 nodes for, in this case, 4 terabytes of data. As we increase the block size, this is the x-axis from 32 megabyte, 64, 128, 256. The performance changed. We can see that for SSD, the blue bar, it didn't change much, which we knew because the blocks that wouldn't affect it that much. But for Lustre, you start to see a big savings. Okay, noticeably bigger savings. In fact, it started to close up that gap. And if we overlay the corresponding number of files, intermediate files that was created, you can see a clear trend that this Lustre performance is trending with. In other words, lesser files, bigger in size, tend to produce better noticeable Lustre performance. Any questions so far on these 3 experiments? I know it's a bit dry. I'm sorry for that. This is not the usual, here's how you tweak the neural network to get this. It's not that. It's kind of, it's for a certain audience.
It's pretty practical, though. Nothing wrong with that. My question is, so what's stopping you? So, you've determined that this large number here for the block size is the optimal number. Is that just where you stop seeing noticeable performance gains? Like, what if you did like 1 million more, right?
You get fragmentation. You get fragmentation. So it's the number of tasks gets chopped down as well. So which is good. I mean, there's always you expect a sweet spot. If you have billions and billions of tasks, the code managing that, the runtime, this procedure managing that will get overwhelmed. So that's not good. If you only have one task, that's not good either because you're out of parallelism. So you want enough tasks on the nodes you have and the number of workers or cores on those nodes to keep occupied. But then you don't want so many such that the block sizes gets too small and then really grinds down your Lustre performance. So that's your trade-off. You have to have parallelism. If you make it too big, you're going to run out of parallelism because each task gets one block. You choose on that block so that it doesn't affect anyone else. So you can imagine the ultimately you just have one big giant block, but then that's no good.
Right, that makes a lot of sense. Thank you.
Mm-hmm. Great question. Any other questions? So what were we able to do? First and foremost, we were able to train a random forest on all 76 terabytes of the data. Okay, this is sort of our great accomplishment on Catalyst of all systems. So if we can do this on Catalyst, imagine what you can do on the latest, greatest systems. So here's on that, and we were able to do it in 12.5 hours, even better. For this case, we follow our best practice, turn on Rdd compression with ZSCD level 1. Okay, on the graph here, which you should be familiar with now, it's just our typical disk utilization. Disk utilization, blue line, and then the orange line is the memory utilization. Okay. Now, by leveraging the detailed Spark log file, we were also able to determine the timings of each stage of the Spark job and superimpose that on top of this plot. Okay. So now this resulting graph gives you a very informative view of what happens underneath the hood during this Spark job. Okay, we used 293 available nodes. That was all the nodes that we can get. I do this a few times because a couple of nodes kept dying on us when we submitted the jobs. So here's what we noticed. Memory fills as data is read from Lustre. Okay, so that's the orange line right here, jumps right up. This goes to stage 2. Once memory fills up to whichever the pre-allocated percentage, then SSD begins to fill up. Okay, this is what we see in stage 5. And finally, the random forest regression is performed from stage 6 to 13. Because in this case, the default level depth equals 4. So bragging about 76 terabytes is great. What interesting questions were we able to answer from this? And this goes back to Sam's question. which is sampling. Do we really need to train on all 76 terabytes of data? And if not, then which sampling strategies are most effective or more effective? In order to answer this question, we need to first establish a baseline performance. So this, in this case, requires some amount of testing data for evaluation. So we split the 76 terabytes into 40 and 36. Here's what we noticed. The overall root mean squared error is 0.002, which is fantastic. Yay. However, when we broke that down into each class, again, that's a little bit tricky because we're talking about regression and I'm talking about classes here. So what am I saying? If we broke it down into each class with a non-zero class, if you will, it showed that the RF model made a lot of errors at predicting failures than non-failures, much, much higher. Okay, clearly this is not ideal. Mispredicting these failures will result in more crashes, and we clearly have a class imbalance problem. Okay, we're somebody talking about zero versus non-zeros. Okay, so going back to the sampling question, rather than just randomly subsample the original data, what happens when we only subsample the majority class? Okay, so the table on the right here shows the per class RMSE across different sampling strategies. Okay, so basically we use all the failures we can get our hands on and only use a subset of the non-failures correspondingly. Okay, when we do that and we increase the sampling strategy, now we're starting to see a convergence. Okay, and more importantly, in this error conversion, more importantly, the error goes down quite drastically from 0.209, from 0.575 down to 209 or 208. Okay, so this is a good demonstration of how can we use big data analytics to help answer some basic questions we may have. In this case, what is an effective way to subsample this data? Yes, you can always randomly subsample, but with a highly imbalanced data set, that may not always be the best strategy. And of course, even if we have a lot of examples of failures, which we're going to look at later on, are they all the same looking failures? If so, do we need all these examples? If not, what are the different classes of failures that we would need examples from to train our model effectively? Those are the questions we're keen on answering. And having this framework and having the ability to do this on this big data to establish the baseline performance was important for us to answer those questions. Now, going to the failure mode analysis. So this is the unsupervised learning. So note that from this pipeline, we did not try to, this was a bunch of function calls. Instead of one big monolithic function, we have a bunch of smaller functions. And of course, we did not try to optimize with any persist calls in between. Okay, you can play that game if you want. It takes up more storage and you know how that goes. So we did not do persist calls, we simply ran it as is. Hence, this pipeline exhibits a much smaller X factor than a random forest use case. Again, we're trying to show you different use cases. Some, like the random forest, blows up quite a bit, others, not as much. So how do we do for this very different use case? The graph here compares SSD performance between the old way doing it and our way doing it. For the runtime, top graph, no difference. Okay, if you cover up the bottom graph, you only look at the top graph, you say, they looked about the same. What's the big deal? There is no difference. You'll be right. If you look at the X factor, you'll notice that it becomes a difference. Now, the difference was not as dramatic as random forest by design, but there's still a noticeable difference. Okay. In fact, the table here shows you weak scaling results at large scale using 10 terabytes on 40 nodes, 20 terabytes on 80 nodes, and 40 terabytes on 160 nodes. Okay. The runtime was more or less constant. It inched up a little bit, but not drastically. The X factor stayed the same. But this held across scale. Here's a corresponding graph. You've seen this already. This took up, for 40 terabytes of data, it took up almost 24 hours, which is a full-time allocated. I should mention that we did not get a dedicated access to the system to do this. We ran this as a regular user. Okay, I think the 160 nodes was the most we can allocate. Of course, on Catalyst, for those of you who know, that 24 hours was the time allocation we have. We ran this under a normal allocation. Okay, so same idea as before, only of course this time because we have a lot more functions, we have many more stages. So as usual, memory fills up, data is read from Lustre and then persisted in stage 2. Same as before. Next, we'll apply the data standardization from stage 3 to 7. This is what happens. And then after that point is k-means clustering. And the default setup for k-means clustering is 20 iterations. So essentially those are the stages you get with k-means clustering. This is from the majority of the stages. And then lastly, the silhouette scores are computed from stages 50 to 53. Okay, so what we were able to learn from this use case. We computed the silhouette scores, which is a measure of cluster quality of the k-means clusters. From the table here, you can see that as we increase the data size, the silhouette scores increased, which indicates that the resulting clusters are more consistent. In other words, higher quality. Now, to see if these clusters actually make physical sense, we take the centroids of each cluster and visualize them on a parallel coordinates plot. That's this complicated looking graph down here, okay? Now, in this case, the coordinates corresponds to the 16 learning features that we use in the random forest, okay? So these are all the mesh quality metrics, like area or angle. So these are the geometric features where we're using to try to train the machine learning, the random forest algorithm. And from that, again, with the k-means of k equals to 2, we want to see, do we get a natural clustering between the failures and the non-failures? Because that's what we would expect. We expect all these failed elements to make a distinct cluster from the rest of the non-failed ones. Okay, and for the ones and of course, this is how we try to find out, are there any ones that we didn't properly label that should have been labeled better? Now, we got this output, so we use a feature importance from the output from random forest to help organize this graph. So now I'm putting my visual analytics hat on. Typically, when you use these parallel coordinates plot, you get this big hairball of lines, and it's hard to make sense of it. But if you organize things, if you use color them accordingly, and organize it, you get a much more better view of things. So here, all the clusters that had the most failures in it, we gave it a blue color. And all the clusters that did not have or has fewer failures than the other one, we gave it orange coloring. So now you start to see a separation between the orange clusters, the non-failures, versus the failed ones. You can see it per feature, per learning feature. Okay, in fact, we know from the random forest output that there were some features that are more important, feature importance computed using the Gini score, than others. In fact, some of the ones may not even matter, which is what you see here. So if you reorganize this parallel coordinates plots and put the important ones up front, you get a clear trend, which is what you see here. So you see condition number, oddity, max angle, skew, they're all very similar in being able to separate the failures from the non-failures. Likewise, you get a flip here between distortion, shear size, min angle, etc., scale Jacobian. Okay, and that's what we're interested in. Are there learning features that we can decipher here that can help distinguish failures from non-failures without us having to say, these are the failures, these are the non-failures. Again, the unsupervised way. Okay, this is what we want to glean from this, learn from this. And this output gives us a way to do it that we couldn't do before, or we could do it only via subsets. All right. Oof. Okay, so that was a very deep dive we just took. Let's come back and discuss some of these lessons learned. First, the data persistence. This is fundamental to Spark. The blessing of data persistence is that it can reduce redundant I/O for multipath computations. The curse is that it can lead to these ephemeral data explosion, more than 12x for random forest. For compression, we can learn some lessons from HPC world. Flops are cheap and data movement is expensive. Hence, any runtime overhead by compression are compensated by the I/O benefits. Also, working with compressed RDDs makes it more likely that your Spark job will fit on the node local SSDs, which is great. But in case you have to spill onto network storage, then first follow our simple strategy of using a hybrid strategy to make best use of SSD and network storage. And second, increase your block size in Spark to improve performance. Okay, and then for the actual machine learning part, data sampling can be effective, especially done in conjunction to reduce class imbalance. And as we just saw, there are certain modes of failures that makes it distinct from non-failures. Okay, I'll leave it up to questions now. Sorry, I took up a lot of time. Any additional questions?
Yeah, thanks, Ming. This was excellent. I'll start us off with a question while others are thinking. I'm wondering if you have any advice for new users of Spark. For example, we have a hackathon coming up. If somebody was looking for a mini project to maybe get their hands dirty with Spark, do you have any ideas for a new user?
Find a system that has no local SSDs like Catalyst. That makes it easier. It'll make your job run a lot faster. Try on smaller problems that can fit, and then turn on compression. Those would be the three simplest things. The last thing is to bother Al Chu, because then he will help you set up the Magpie. So the new user will have to get the environment set up. It's not hard. You just have to plug your Spark job script into a Magpie setup so that you can run it. This has been done already. Al Chu has done a great job setting this up. So get a hold of Al Chu, say, hey, I want to do this with for the data science challenge or whatever it is. What can I know? How do I get Magpie running on Spark for me and running on Catalyst system for my project? That'd be a very simple way to get things started. And then just try out a couple things. Turn on the compression is very cheap, very easy to do, just one option.
Great, thanks, Ming. We've got a question in the chat from Grant. What format is the original data? He's interested in Hive partitioned Parquet specifically.
The original data, we use a Python interface with just a NumPy file, which is a simple straight up NumPy file, if I remember correctly. We did not try any of the other specific formats, although I don't see any reason why we can't do that. Again, once you read it in, the first reading in step off Lustre, that was a big part, but after that, it's all handled internally. In fact, we have very little say in what it is after that. So this is why showing you those stages becomes interesting, because once you read it in, everything else is done for you by itself. Which format the data is in initially does not matter as much as people think it does. This is sort of the subtle takeaway from this. And this kind of, a lot of people argue, is it Parquet? Is it this versus that? After you read it in, that's just the first few hours of time. And maybe you can squeeze something out of it, maybe not. Because once you bring it over onto your node local SSDs, that's when all the computation happens. So the savings, so if you have, Spark works with those formats, you use them as is. The ones we use in NumPy, which through a Python interface, work just fine. But that part, the part that comes off of Lustre, the slow part, gets read in, persisted. After that point, it doesn't matter because it's persisted. That persistence saves it and cached it, and now it's all internal formats. We have very little say in it. Does that make sense?
Hi, Ming. This is Grant. Yes, that
Hey,
makes sense. In my specific case, we work with similar volume sizes, but one of the things we do often is complex SQL at the beginning to filter or transform the data. And I think that's where in this case, and it sounds like it should just work. We'd get that advantage in stage 0 by reading in less data to begin with, especially push down predicates work, which they should work fine in that environment, given it looks like Magpie supports Spark 3.x.
I think so. Yes.
So yeah, I mean, so to restate that, I mean, like in our case, what we might do is we could have as much as say 60 terabytes of Parquet, which is already columnar compressed, which could be exploded, would be probably on the order of 10 times as large.
Yeah.
But we would be using its partition by keys that we use frequently to subset. So we might only read in, say, 5% of the data for a particular computation.
Yes.
And
I
then
see what you're saying.
the put down predicates should filter to where we don't even do the IO on the, it can just prune out large chunks of data and never even decompress or read them in.
Yep.
So
Yeah. Yep. I hear what you're saying. That makes sense. That makes
so
sense.
to translate, I'm very excited.
Yep. Cool.
All right, well, I think we've exceeded our time block here, so we should go ahead and wrap up. Thanks, Ming, so much for taking time out of your day to come and talk with us. Presented some very interesting work here, and I imagine lots of folks on the call will reach out to you with some follow-up questions of how
Yes.
they might integrate these ideas into their work. So yeah,
Absolutely.
thank you very much.
Yep. You're welcome. Thanks, guys. I appreciate it.